Hey everyone, it's Alex again, and today we are going over a big topic. This topic will be just like Ohm's Law. It will be persisting throughout the entirety of this lecture series, and I found a new tool on GoodNotes, and it's this laser tool, so now it won't look like a discombobulated voice, just pretending to point at things that you can't see. So let's get right into it. So we have KCL and KVL. So what are these? So this dude named Kirchhoff, you can do some research on the guy. I really don't know. I just know how to apply his laws. We have KCL, which is Kirchhoff's current law, and KVL, which is Kirchhoff's voltage law. Now, let's just get right into it. Kirchhoff's current law is the sum of all the currents entering or leaving a node must equal 0. Or, mathematically, and very simply, the sum of the currents equals 0. Now, we'll get into what this word means in a little bit. Kirchhoff's voltage law is the sum of all the voltages around any loop equals 0. Now, once again, the mathematical representation of this law is just this guy. And for our intents and purposes, this is always true. Okay, so everything that we're going to be doing, all the tools that we're going to be learning in the next few lessons are going to stem from these laws. So I'd say commit them to memory, but you really don't need to because you're going to be using them so much. So let's define those words that I circled in pink. So right here we have a diagram of KCL. Now this right here, this is a node. And you can think of a node as a junction between between wires. I believe that's politically correct. But basically, yeah. So currents go into these nodes like so, or out of these nodes like so. And so right here, this navy blue one is going into the node, and this navy blue one is going into the node, and then this red one is going out of the node. Now, what is this pink stuff here? Okay, remember in last video I said, or 2 videos ago, I said that we're the ones that come up with the sign convention. Electrons don't care if they're negative or if they're positive. Currents don't care if they're positive or negative. They do have a direction though, and we need to be careful of what we call that. Now, this also confused me greatly when I was taking this course, and basically the rule of thumb and the way that I'm going to be doing this for the rest of the lecture series is that currents leaving a node are positive. Okay, so this is super important. And likewise, currents entering are negative. Now, it's kind of like, you can have a 0 or a 1. That's how a computer knows things. And a 1 means yes, and a 0 means no, or something. It's just some representation of the direction here. And this is the naming convention that we're going to use for the rest of the time. And you can be a weirdo, and you can say that entering the node is positive, and exiting is negative. But all I ask you to do is be consistent. I'm going to be doing it. Leaving, that's how my professor taught me, and he was super he really liked doing it that way, and everything that he did was that way. So if it isn't that way, then it will be way too confusing. So if you can see here, these pink ones, they're all going out, right? And you can see here, these guys right here are just the opposite of these pink guys. So this is just the same node with the magnitudes of these currents. So you can think of these magnitudes as like just going out. And so you would just have like, the sum of these currents, and then we can call this guy I1, I2, I3. And so it's I1 plus I2 plus I3. And then here from this actual circuit, like we know which ways the currents are going, so we can assign a negative onto I1 and a negative onto I3. And this should equal 0. Okay? So that is KCL. Now, KVL. All right. So I have right here, what is a loop? So we defined a node as like a junction. A loop is any closed path. As you can see here, there is a closed path for current to flow. Okay? And this guy right here is I, current. And we can say, this guy is arbitrary. He can go this way also. But depending on, and once again, just like here, you have to make sure that you're consistent and you keep it going. So like, for example, if this was a resistor, right? This one doesn't matter. It would just be plus and minus. But what if this was a voltage source right here? Well, then it would be a positive power right here going through it, and so on and so forth. And that's how it's going to be. So this guy is charging. Okay, if you're going to do it like that. The negatives will present themselves as to what the actual configuration of this is. And that might not make sense right now, but once we do a bunch of practice problems, hopefully you'll get the intuition for this soon. So the idea here is that every single one of these components, we don't know what they are. They can be any kind of source. They can be, any kind of source, any kind of resistor. They all have voltage drops. Okay, now once again, everything about this is about convention. So right here I'm drawing this little symbol, and this means ground. Okay, or GND. You'll see this on like circuit sheets and stuff like that, PCB design and whatnot. But here we call voltage as 0. Okay, you can call this spot right here ground if you want to, or that spot, or this spot right here, or this spot right here, or right here. Okay, the idea of choosing a ground is to get as many components to a 0 potential difference that you say, because 0 is very easy to work with. When you're doing all these equations and stuff, we're going to be multiplying by, or we're going to be multiplying, subtracting by some kind of voltage, and you want to subtract or multiply by a 0. Okay, it just makes the math easier. And so when you do this guy right here, you're going to, you can walk around all of this, and the amount of voltage increases, right, will be the same when they add up. The amount of increases is supposed to add up so that it cancels out with the amount of decreases. Okay, so like if you were to think about this, we have let's say component 1, 2, 3, 4, and 5. You could say that we started on an XY plane right here, and we have 0 volts. Say that we started at that point right here. So we've got, 0 volts, and then all of a sudden we have this voltage increase, and obviously it's not going to be a completely straight line, vertical line, because then that would mean that it was instant. And then say that number 2, so this is number 1 right here, component number 1, and then you go here, and then component number 2 increases the voltage, then component number 3 increases the voltage, and then all of a sudden component number 4 decreases the voltage because it's some kind of resistor, and then number 5 furthermore decreases it back. And you can see here that the difference between this point all around the guy is going to be back to where it started, 0 volts. So to make that in math form, the sum of the voltages of V1, V2, V3, V4, and V5 is going to equal to 0. And we're going to see some examples of that in the next video. But yeah, that's KVL and KCL, two of the most powerful laws. So right now what we have in our arsenal is Ohm's law, KCL, and KVL. And these are going to dictate everything that we're going to be doing from now on. Literally everything. Okay, that's it.